Okay, hi everybody. My name is Connor Bush, and this is my homework for submission for part D. So I have my iPad right here, and we're gonna kind of walk through this last part. Just to kind of give a little recap of what's going on here. We have two tanks in series where we have this flow coming in called QC. We are controlling that. That's what the C stands for. And then we have the second tank. So it has the flow coming out of tank one, going into tank two, we call that Q2. So we are interested in having a set point for our height in tank two. So that's our height to set point. Um, and then we are going to use a controller to sort of modify what sort of flow rate situation we need to maintain where we want our height to reach once we hit steady state. And in terms of a transfer function, so we have an input of QC, and that gets dealt with in GP1, our first process transfer function, and then the output of that is Q2, and then goes through again another transfer function, and then the output there is H2. So that is sort of the forward transfer function loop. Before here, we have our controller, and then there's a backward situation where we have our measurable device. However, this is sort of what our process transfer function looks like. And then if we go into Python, we can sort of see what we want to do for part D1A. I can stop sharing here and jump right into my computer. Okay, so we're back here in Google. So part D1A is we're generating 50 synthetic data points for the step response of the previous two tanks in series for 15 seconds. And then we want to add a normally distributed error around each value with a standard deviation of 0.02. So what that looks like, if we this is our code that we're working on in parts B and C. We're going to we're going to start working right around here. So we want to create a new time plot. We'll call it TXEXP for experimental time. Sorry, here in my mouth. So we want 15 data points, or from starting at 0, going up to 15 seconds, and then we want 50 data points. To get that sort of step response we are looking for, I previously had our transfer function from QC to Q2 and then Q2 to H2. I combined all of that. So our QC to H2, we can call this our process transfer function, or our GP. So to get our step response, we want our time to be using this experimental time here, and then the results of using a step function are two arrays. We have our time and then our heights that we're going to be getting. So we're not really interested in having that time array, so we can leave that blank, and then we can have these experimental heights saved under as H2 EXP. To include our sort of normally distributed error, we are going to use a random number generator. So that looks like this. So our seed, we can just enter any sort of random numbers there. And to get those new values, we want to do random number generator dot normal, where our location is surrounding those points that we receive from that step response. And then the scale is where we can say what our standard deviation is. So that's going to be 0.02. So if we save all of this, we can go into plotting. So I believe we are down to figure 4, correct? So we're gonna make a new scatter or subplot. And then we're gonna add this scatter plot. Our X is going to be that new experimental time scale from 0 to 15, 50 points in between. And then our Y is going to be our new H2 experimental values. And then we're going to update the mode to be markers since it is experimental data. And then we're just going to update the layout as per usual. And then make it a dark template just because it's easy to on the eyes. So here, as you can see, on our x-axis, this is our time scale from 0 to 15, and then this is our heights in response to that step increase from the set point. So this is kind of like showing how long it takes to reach that sort of set point. So if we jump back into my iPad, I can start explaining how we're going to be able to fit the data using this first order plus time delay model by using a minimization function of the sum of squared error between our FOPTD model and this data that we just created. So let's hop back over to my iPad really quick. Okay, so in general, we are looking, so we have a 2-tank system, so it's not necessarily a first order, but generally those follow the second order or higher order follows this sort of S curve. Our curve is going to be, we want to model after first order, so it's going to be a sort of exponential decay function. And as you can see, there's this difference here between the origin and where our function begins, and that's our dead time or theta. So we can model, so this S curve is originally modeled by some proportional constant k multiplied by 1 minus the exponential of negative time over some time constant tau. But if we want to update that using this sort of dead time phase shift, we just update that as such here. So we're taking the difference between the time and theta and still divided by our time constant tau. So this is sort of our FOPTD model. So we can go back into Python and code that and then take the difference of the sum of squared errors. And then we can use a minimization function to get the k value, the tau value, and our theta value. So now what we want to do is we want to make a function for this FOPTD model. So we are going to have one vector being inserted into this function. And as I was saying, we want to find a k value, a tau value, and a theta value. So our y, or our output, is going to be equal to k multiplied by 1 minus the exponential function of negative, because it's an exponential decay, our time plot, our new time plot, minus our theta value to account for that shift. And then still within that exponential is our tau value. And I need to make sure we are using JNP.that. And then to consider when we have that dead time, we want our function to be 0. So when we return, we can use this JNP.where. So where our time values are less than theta, we want our function to return 0, and then otherwise just that y function. And so now that we have that, we are going to want to have a sort of initial guess for all these values. So we're going to call that v guess, and it's going to be a tuple. So our k value, let's just guess for 2, 4 for tau, and then theta, we'll just say 1. And then if we make our sum of squared errors function, it will also take in a vector. So what we're going to be doing here is we want to take the difference between our experimental data points that we created, and then we're going to subtract that from our model with that v input. We want to square this difference, and then we want to take the sum of that, and we want to return that. And then finally, when we want to go to minimize, we're going to have to update this SciPy to optimize. So we also are importing minimize. If we come back down here, we can minimize our sum of squared errors, and then our initial guesses are our v guess vector. We can store this as a variable called res for results. And then if we look, we have 3 values. So this is our k value, this is our tau value, and then this is our theta value. So we can say k, tau, theta are all equal to this. So now what we want to do is we want to add a new scatter plot to the existing one up here, where the x is our t exponential, our y is going to be our FOPTD model, where our vector is going to have these inputs here. So we can just say res.x, and then we want the format of that this new scatter plot to be in lines because it is a model. So if we take a look at what this looks like now, you can see that from our dead time, our theta, our curve sits at 0 and then matches this data in a sort of negative exponential curve here. So that covers what we're looking at for part D1B when we want to fit this data into a model using a sort of regression approach. So now we want to determine the optimal ITAE controller gain and reset time. So ITAE is the integral of the time-weighted absolute error. So it's sort of this relationship here, and we want to determine the KC value and the tau I value for a PI controller. So previously, in the other parts, we were essentially looking at a PI controller because we set the tau D to 0. So how we're going to be doing that is we look at the type of controller using the set point type of input, and then there's these 3 relationships here. So we have our A and B from this table, we have our theta and our tau value, and our k value from what we just used in the FOP TD optimization or minimization calculations, and then we can grab that KC value, and then here, similarly, we can grab the tau I value. So to do this, we need to essentially just divide all of this by k, our big K that we just got to get our KC value. So our KC is going to be equal to all of that y divided by our k, and then we start with A. So our A in this proportional portion is 0.586. This is going to be multiplied by theta divided by tau to the power of b, which is negative 0.916. So this is our KC value, and then our tau I value is going to be equal to this entire right-hand side divided, or tau divided by this entire right-hand side. So we can begin with tau divided by our A value. So now we are in the integral mode, so 1.03 plus our B, in this case, it's negative. So minus 0.165 times the quotient of theta and tau. So that is our Kc and tau I value. So if we print those, we can see that our Kc value is around 1.09, and then our tau I, or time interval, is around 3.61. So now that we have those two parameters calculated, we can simulate closed loop response using this PI controller to a step change in set point. So essentially what we're looking for here is we're going to sort of ignore what we had originally just as inputted for our controller gain and time interval. We'll keep tau d at 0 to make sure that it's just a PI controller, not PID. We don't need to print that. That was just for the sake of that. And then this we renamed to be TF process. So if we look at what our step response is to change in set point, we can see on this x-axis, this is time, and then here is our second tank height. So this illustrates that step response, and then we reach that set point fairly quickly, and it is a very steady. Obviously, you can see essentially just a line across. So that is our simulation of the closed loop response, meaning, so if we kind of go back, our transfer function, our forward direction is that PID controller, our tau I we set to 0. We updated these two parameters. Our Kc is from here, our tau I is from here. And then the process is what I was explaining. So our GP1, GP2, that is all multiplicative, and we calculated that up here. That hasn't changed. And then since we are looking at that closed loop, we want to look at our measurable transfer function. And in this case, we're just multiplying by 1. So this is the backwards direction of multiplying by 1. And then still have that step response. And that is the result. So that covers that portion, D1D. And now we want to look at the Bode frequency response analysis. And we're going to determine the phase margin from that PI controller, what we just did in D1C. So if we carry this to the very bottom and look back at our Bode plot, you can see that our frequency versus phase lag diagram never hits that negative 180 phase lag, which is good, but we only get to 10. So if we increase our sort of range there, and do NP log space, going from -2, meaning 0.01 to 2, or in the log space situation, it's 100, and then do 50 points for that. And then if we specify that we want these frequency values, we can do that. So that extends our x-axis as such. And as you can see, we still never hit that negative 180. It's almost as we're reaching a limit. So to determine our phase margin, we come here, look at when there are 0 decibels, meaning that inside the logarithm, it's 1, which is our amplitude ratio. So when our amplitude ratio is 1, or our decibels read 0, we come down here, and we're essentially at negative 120 degrees, and our phase margin is just the difference between here and negative 180. So our phase margin is essentially 60 degrees. And that kind of covers what we need for the phase margin. And in terms of stability, our system is extremely stable when we are at 1. This value is negative. And then if we look here to confirm that, our input amplitude is much greater than our output amplitude, meaning there's no amplification in our response to our controller, meaning our system is indeed stable. There's no increase in oscillations. Yeah, so that kind of concludes everything we need for homework for part D. Thank you.